next concept to be looked at is the situation where sometimes derivatives are easier to solve in a different way or easier to calculate a different way than what we've been doing up to this point. And I think my idea can be best illustrated with an example here. What if we have the equation 4x squared plus 3y squared equals 6? And our goal is to find a derivative of this function, okay, so that we can write the equation of a tangent line, or we can find the slope at some point, or something that we've already done in the past. Well, what we have done, or what we have been doing before, is what we would call explicit differentiation. Okay? And what it means to do something explicitly, it means that we would want to go through and solve this equation for y and then take the derivative. And that's the first thing that I want to do, is if this was our question and you were supposed to find the derivative with respect to x, how would we do this? Well, what we would do first is try to solve this equation for y. So step one would be go ahead and subtract the 4x squared piece over to the right side. Then we would go through and divide everything by 3. And then we would go through and square root both sides. And so we would get an answer of the square root, and I'm going to go ahead and take this 3 into both pieces here. This will be 2 minus 4/3 x squared. Okay? And if we have an equation like this, if we do these one at a time here, if I just look at the positive one for right now, do we know how to take the derivative of the square root of some function? And the answer is yes. We called it the chain rule. Okay? So we have a way of finding derivative if we go through and solve this equation for y. Now, I want to go ahead and finish this problem off, because here in a minute I'm going to show you the alternative approach, which is a little faster, and so that way when we get to the bottom we can compare answers and see that they're exactly the same. Okay? So what would this derivative be if we were to go in and take the derivative letting x be our independent variable? Okay? Well, how do we take the derivative of something raised to the 1/2? Well, we put the 1/2 out in front. All of our piece inside the square root is to the negative 1/2. And then the chain rule comes into play, where we need to multiply by the derivative inside of this function. And the derivative of 2 is just 0. And the derivative of this thing would be negative 8/3 times x. Okay? And we could do some simplifying here, but I'll just leave it at this stage for right now. Okay? So this is one way to find the derivative of this function, is to solve it for y and then take the derivative. Okay? Now, herein lies the difficulty. We will find in this section, and as we go through the book, there will be some functions that either, one, they will be really difficult to solve for y, and so then the derivative will become very, very difficult, or the second part is that you will not be able to solve it for y. You just won't have a choice. There's no way to solve it. Okay? And so we need to have another way of taking derivatives if we fall into one of those two categories. And the name of that other function, or that other process, this one is called implicit differentiation. Okay? And implicit means we're not going to solve it for y. We're just going to take the derivative of the function the way that it is presented to us. And what we will find out is that implicit differentiation is a lot nicer than this explicit form here. Okay? All right, now, before I get into doing this one with implicit differentiation, I need to talk about the process here just a little bit. What does it mean how can we take the derivative of something when we don't have it solved for one of the variables or the other? Okay? Going back to this idea of the chain rule. Okay? If I gave you a function like 4x squared plus 8 raised to the second power, okay? Would you agree that this function in here, this is a function of x, meaning that x is the variable in here? Okay? So what I could do is, instead of having this function here, I could just say, if I just want to generalize this idea, I could say, well, this is some function of x. This is some f of x. Okay? And all I want to do with my f of x is I just want to square the function. Okay? So if I was to rethink about it, instead of actually knowing the equation, what if I don't know the equation? What if it's just some f of x? Okay? Well, how do we take the derivative if we know the answer, if we know the equation? Well, we do the chain rule. Okay? The derivative would be, the 2 would come out front, we'd have 4x squared plus 8 to the first, and then we'd have a derivative of 8x for the chain rule on the inside. Okay? That's our chain rule. We've done this for quite a while now. Okay? Well, what if we don't know the function inside? What if it's just some f of x? Can we generalize this idea of chain rule? And the answer is yes, we can. Okay? We would do a very similar process. I would still bring the 2 out in front, but if I don't know what this function is, the best that I can do is just say, well, whatever the function is, I would raise it to the first power. Okay? So all I'm doing is trying to say, well, what if I don't know this? How can I still work the problem? Well, I would still bring the 2 out front, function to the first power. And then what do I need to multiply over here? What's the 8x coming from? Well, that's the derivative of the function, isn't it? Okay? So that is either f prime of x, you could write it that way, or you could write it df dx or dy dx, or any of those notations that we've used before. Okay? But the big idea that I'm trying to get at is that if we have a function of x in here, okay, we can still take the derivative, we just can't quite be as specific. Okay? All right, now, that's the key idea behind implicit differentiation. Okay? Let me rewrite the function over here. 4x squared, 3y squared equals 6. What we are going to do is, we're saying this is a good equation, so we want to take the derivative of both sides. So if my equation is good, if I take the derivative of both sides, that's a legal step. Okay? If I start over here, okay, what's the derivative of 4x squared? Well, x is my variable, so there's no difference into what I've been doing in the past. The derivative is still 8x to the first, because x is the independent variable, so nothing has changed here. The change that we will see is that now we want to take the derivative with a y term in it. Okay? Now, here's my question. Could I solve this equation for y and turn it into a function of x? Yes, we just saw that we could do that here. Okay? But we don't really want to do that because that was the difficult way to solve the problem. So what we're going to do is we're going to use that idea that I just erased here. We're going to treat this function y, and I'm just going to rewrite it here, as some function y of x that's being squared. We could solve this function with just an x in it. So I'm going to treat it kind of like the f of x. I'm going to treat it as a y of x. Okay? Now, how would I take the derivative of this thing? Well, what would I do with the 2? Comes out in front, sure. 2 times 3 is still 6. Okay? My function y of x is now to the first power, isn't it? So 6 times y of x to the first, and then what do I need to multiply by because of the chain rule? Well, I would have to take the derivative of this inner function. Whatever it is, I would have to take its derivative, and I'll just call it dy dx. Okay? This is the derivative of this piece up here. It's saying that if I knew what the function was, if I actually solved it for x, okay, or solved it for y so that it could look like an x term, okay, if I was to take the derivative, this is what it would look like. I'd bring the 2 out front, whatever the function would be to the first, and then I would have to multiply by the derivative of the function. Okay? All right, so this is the derivative, and this is good enough for right now. Now let's go to the other side. What's the derivative of 6? 0. Okay? And this is a common mistake. Don't just leave it as a 6. Make sure you take the derivative of that side as well. All right. This is what we mean when we say implicit differentiation. We don't actually solve the function for y. We just take the derivative and pretend like we could solve it. If we could solve it, that's what it would be. Okay? Now, what are we interested in solving for? Well, over here, we always want to solve for dy dx. Same thing applies over here. We want to now solve this algebraically for dy dx. Okay? So if we were to do that, what would be the first step to solve it? What could I do with this thing over here? Could subtract it over to the right side, sure. So I could have 6. Now, I'm going to also mention this right away. Usually we don't write it y of x. We just kind of in our mind understand that, yeah, this is a function of x. So I'm just going to write it as a y. Okay, so 6y to the first. Okay, dy dx equals negative 8x. I just subtracted the 8x over to the right side. Now, if I want to solve for this, what do I need to do with the 6 and the y? What operation? Divide them off, sure. Okay, so if I divide both sides by 6y, I get dy dx equals negative 8x divided by 6y. Okay? Now, here's the big thing. We need to make a comparison. We need to see, is this derivative, dy dx, is it exactly the same as this derivative, dy dx? And on the surface, the answer looks like, well, no, they're not even close to the same thing. But if we look a little bit closer, we're going to recognize that they are exactly the same thing. This function is solved completely in terms of x's. There's no y's over here. Okay? This one has a y in it. Okay? So if we were to go back and replace that y with all of this right here, and then compare them, we should see a match. Okay? So let's go ahead and do that. Negative 8x divided by 6, and then the y was the square root of 2 minus 4/3 x squared. Okay? Now let's make a comparison with this function and with this over here. Okay? Do I have a negative 8 up in the numerator somewhere? Yes, I've got a negative 8 right here, and I got a negative 8 right here. So those match. Do I have an x up in the numerator somewhere? Yeah, this x is really could be placed up in the numerator because it's multiplied, right? So this x matches up with this x right here. Okay? Do I have a 6 in the denominator? Yes, I have a 2 times 3, which is 6, matching up with this 6 right here. And then the only thing left, if I was to take this and rewrite it as in the denominator as to the positive 1/2, would it match up with that answer down over there? And the answer is yes. Okay? So these two are a perfect match. And it may not appear to be right away because I had to go through all the details, but this is actually a much faster way, and it's also a much nicer answer. It's a lot cleaner of an answer as opposed to this answer over here. So implicit differentiation is the way that we want to go here. Okay? Now, let's look at another example of implicit differentiation. And let's just see if we can skip out some of the details so you see how this works. What if we've got the function x cubed equals y squared plus 4? We want to solve this, or we want to find the derivative of this thing. The question is, find dy dx. Okay? All right, so we're going to use implicit differentiation. We don't want to solve this for y. Okay? All right, what's the derivative of the left side? 3x squared, right. Okay? Nothing fancy, nothing changes here because there's just an x on this side. So just normal derivative. Okay, over here, what's the derivative of y squared? Okay, the derivative of y squared is 2y, but then what do I need to multiply by because of the chain rule? Well, I would have to multiply by, good, dy dx. I would have to multiply by whatever the derivative of this function y is. Okay, what's the derivative of positive 4? 0. Okay, so we're done. Or at least we're almost done because we've got the derivative part done. The only thing left to do is we usually want to solve for dy dx. So how would I solve for dy dx? Sure, just divide by 2y. There's your answer. Okay? Much faster than solving for y and taking the, solving for y, taking a more complicated derivative and then having to clean it up. Okay? So this is a much nicer way to do the problem. Okay? This is our first derivative. Okay? All right. Next example. And this is just where we have to be a little bit careful. 2 plus q squared equals 1600. Okay. Here's a function with two different variables. Now we've got p's and q's. And we've seen a lot of applications with this. Q has been standing for what? The quantity or the number of items, and P is the what? The price of the items, right, okay? And those are usually related. How many ever items you have, that affects how much you charge for the items. Okay. Part A of this question says to find dq dp. And then part B of this question, which I'll do over here, says to find dp dq. Okay? And we can actually do either order. When we're doing implicit differentiation, we can think about either one of them as the independent variable. Okay? Now, here's just where we have to be careful. We just have to remind ourselves which one of these is kind of like the x and which one's kind of like the y. Okay? Which one of these two in part A is more like the x variable? The p, right? Because we're used to doing dy dx, aren't we? Okay, so we're going to treat the p like the x. All right, so what's the derivative of 2p squared? 4p, right. Do I have to worry about any like dq, dp's or anything like that over here? No, because I'm treating this like the x. This is the independent variable, so the derivative is just 4p. All right, what's the derivative of q squared? 2q. Now, this time, do I need to worry about a dq, dp or a dp, dq? Yes, because this is kind of like my y, and so I need to multiply by dy dx, or in this case, it's dq dp. Right, I'm letting p be the independent variable, so I have to do that multiplication. Derivative of 1600 is what? 0. Okay? And so I can go through and now just similarly to what we've done before, I can do a couple of algebra steps, and dq dp would be negative 4p divided by 2q. And I could actually cancel off a 2, but it's not going to matter that much. Okay? So this is the derivative of q with respect to p. Now, what does this mean? What if we were to interpret this? Now, I know I didn't give you a real problem here, but if we talk about prices in dollars and q is the number of items, what is this derivative telling us? Well, this is telling us how if we change our price by a little bit, this will tell us how much our quantity will also change. This is change in quantity per change in price. Okay? So the label for this would be something like items per dollar. So if I up the price by $1, how does that change the number of items? Okay? That's what this one tells us. Okay? All right, now let's do the other derivative. Let's do dp dq. Let's go the other direction here. Okay, so now I'm thinking about q like the x. All right, what's the derivative of this? It's still 4p, but now this time I have to multiply by what? dp dq, right, because I'm letting q be the independent variable. Good. Okay, what's the derivative of q squared? 2q. Do I have to do any multiplication on this one? No, because q is my independent variable, so I've already done that. Okay, the derivative of 1600 is still 0, and I can do some similar algebra to the other ones. dp dq is negative 2q divided by 4p. What would be the label for this derivative? This is dollars per item, right? The price label over the quantity label. Good. So this is dollars per item. Okay? So what this is saying is if I start to sell more items, this would describe how the price would be changing. Okay? All right, now, one more thing that I'll just point out. What do you notice about the two answers, dp dq and dq dp? They're just reciprocals of each other, right? And that kind of makes sense. You know, if we solve for this one, if I was just to flip it over, shouldn't that match up with dp dq? Yeah. So really, it's not necessary to solve, you know, if you get a question where you have to do both of them, you really only need to solve it one way and then flip it to reciprocal it to find the other one. Okay? But just be really careful. Make sure that you understand which one of the two that they're asking for, because you do get a different answer depending on which one they're looking for. Okay? All right, good. So there's that example. Okay, let's do this one next. This is an application from physical sciences here. S cubed, minus 4st plus 2t cubed minus 5t equals 0. Okay, so here's our function. It says the position of a particle at time t is given by s. So t is our time component, and s is the position or the location of the particle at that time. So if I was to go into this equation and plug in t equals 0, that would tell me the position of the object when I start looking at it. If I plug in t equals 1, that'll tell me where is this thing at 1 second later, or 1 minute later, or whatever time is in this problem. Okay? The question that they want you to find, they say find the velocity ds dt. Okay? We saw this in earlier applications this semester, that the velocity is the same as the first derivative, the position divided by the time change. Okay? So that's what this question is. Use implicit differentiation. Let's find ds dt. Okay? So remember, which one of these is kind of like my x? The t. All right, so we're going to think about t as like the x. All right, so what's the derivative of s cubed? 3s squared ds dt. Good, because s is kind of like my y. I've got to do this multiplication. Good. Okay? All right, well, we'll go ahead and do this one next. This one's going to be a little different. We haven't seen this yet today. Notice I have a function of s, and then I have a function here with t. Okay? Which derivative rule will I have to use here? When we have two functions multiplied by each other, we have to use what rule? Product rule. Okay? So this will actually be a product rule. And like I said, we just haven't had this before today. I need to somehow split this up into a product. And there's more than one way to do it, but I'll go ahead and let this be the first part of the product. This will be the second part of the product. Okay, now let's run through the product rule. Okay, product rule says you take the first piece as it is, and you multiply by the derivative of the second. Well, what's the derivative of t in this problem? 1, and do I have to do any multiplication? No, because t is like my x. Right, so this is just negative 4s times 1. Okay, plus the second variable, or the second part of the product, times the derivative of the first. Well, what's the derivative of negative 4s? Negative 4. And then because it's an s, ds dt. Right. Okay. What we're going to find out, and it'll take a couple more problems, but I think you're going to start to catch on. It's really, the idea is that if you ever take the derivative of the y term, that's the one where you have to multiply by ds dt. Okay? If you do a derivative with the x term, kind of like the x term, you just do the same old derivatives we've been doing before. Okay? All right, so we're done with this, we're done with this. Okay, what's the derivative of 2t cubed? 6t squared. Do I need to do any chain rule multiplication? No, because t is my x variable. Okay, what's the derivative of negative 5t? Negative 5. And the derivative of 0 is 0. Okay? So I've got this all set up. Now, the question wanted me to solve for ds dt, so I have to do a little bit of algebra here. Now, the way to solve this for ds dt is I want to get all the terms with ds dt's on the same side. Everything else goes to the other side. Okay? So I'm going to leave these terms over here, and on the right side, I'm going to have a positive 4s. You know, if I add this over, it'll be a positive 4s. If I subtract this over, and if I add this over, I'll have 4s minus 6t squared plus 5. Okay, just move everything over to the right that does not have a ds dt in it. Okay, now why did we want to do that? Well, what can I factor out of these now? I factor out the ds dt, exactly. So if I take out ds dt, okay, what do I have left from here? 3s squared. What do I have left from here? Negative 4t. So that's why I keep all these terms on one side. Then I have the ability to factor, and now how do I solve for ds dt? What do I do with this here? Divide it over, exactly. Because it's multiplied, I have to do the opposite, I have to divide. So ds dt is 4s minus 6t squared plus 5 divided by 3s squared minus 4t. Okay? This would be your answer here. Okay? Now, notice this is somewhat complicated, but if we were to try to go back and solve this original equation for s, this would be even a much bigger mess, because wherever we would see an s in here, we would have a really complicated function. Okay? So yeah, this is the preferred way to go. Okay? All right. Now, let's take the next step here. Let's see. What if we've got this one? X squared e to the y plus y equals x cubed. And again, the goal is to take the derivative of this thing without having to solve for y. Now, this is an example where we can't even solve this for y. This has got a y in the base. This one's got a y up in the exponent. Algebraically, we don't even have a way to solve this. So we have to do implicit. Okay? All right. What rule will I have to use out here? I'll have to do product rule again, right? Okay, just like the example that we just finished up. All right, so let's do product rule. And if they don't tell you, you can pretty safely assume that you're supposed to find dy dx. Okay, I mean, very, very rarely would we ever care to know about dx dy. Okay, all right, so we start with our product rule. The first term is x squared. What's the derivative of the second term? E to the y, and then what? Times dy dx, right? Because I took the derivative, y was the variable, so that's why I got to do a dy dx. Okay? Plus the second part of the product rule says, I write the second term, what's the derivative of the first? 2x. Do I need to multiply by anything? No, because my variable was x. The only time I have to multiply by something is when my variable is the other term, the dependent variable. Okay. Plus, what's the derivative of y? 1 dy dx. Yes? Okay. And what's the derivative of x cubed? 3x squared. There you go. Okay. So this is the actual calculation of the derivative. Now again, the last step is to solve for dy dx. So we leave all these dy dx terms on one side. So I subtract these over to the right. So I've got this 3x squared already over here. If I subtract 2x e to the y, and then over here I do some factoring, dy dx, so x squared e to the y plus 1, if I do the factoring, and then my last step is just divide. Okay? Now, I think you're going to get pretty good at these as well. You won't necessarily have to write out all these algebra steps. You know, once you get to here, I don't think it'll be too big of a jump for you to be able to do all your adding and subtracting over to one side and then do your division of the factored terms at the same time. Okay? So it'll be this divided by this. Okay? There's your answer. Okay. All right, next example. Let's see, which one do I have here? X squared plus y squared equals 100. Okay? Not a difficult problem to do, but now we're going to take one more step up, is we're going to write the equation of the tangent line that goes through the point 8, negative 6. Okay? Now, I don't know if any of you know this geometrically or not, but does anyone know what this is the equation of? What picture is this? X squared plus y squared equals r squared. This is a circle, okay? So this is just basically a circle centered at the origin that's got a radius of 10, because the square root of 100 is 10, okay? They want us to come in, and wherever 8, negative 6 is at, so somewhere down here, they want us to write the equation of this tangent line that just touches right at that point, okay? What are the two things we need to know to be able to write the equation of a tangent line? Got to know a slope, and we got to know either the y-intercept or some other point. And in this case, we'll just go ahead and use the point they gave us. That'll be easier. Okay? So I have the point. The only thing left is the slope. Well, how do we get slopes? Through the derivative, exactly. So now we need to go through and take the derivative of this function. Let's use implicit differentiation to accomplish that. Okay, what's the derivative of x squared? 2x. What's the derivative of y squared? 2y dy dx. And what's the derivative of 100? 0. Okay, so I really quickly can go ahead and do this. Now, I have two options at this point. One of them is just like I've been doing, I can solve this equation for dy dx. Okay? However, it's not really necessary if we're only, here we're looking at all the x's and y's. We don't have a specific one we're looking at. Here we have a specific one we're looking at. So if I want to, I could just sub in the x and y values and then do my solving. Okay, so it's up to you. You'll get the right answer either way. Okay, if I sub in my x here, so 2 times 8, and if I sub in my y, okay, and then solve for dy dx, that will be a way to find the slope. Okay? Let's see. So I've got 16 minus 12 dy dx equals 0. If I subtract 16 from both sides and then divide off the negative 12, that's my slope dy dx. Okay? Looks like if I simplify it, it comes out to be 4/3. Okay? It's good that this is a positive number because we can clearly see that on this circle this should be a positive slope. Okay? All right, now, what's the final equation? Y what? Okay, y plus 6 equals 4/3 x minus 8. Sure. Okay? Just the same equation of tangent line before. Y minus the y coordinate equals the slope, x minus the x coordinate. Right. Okay? If you want to, you could go through and solve this for y. Okay? It's not necessary. If you want to leave it this way, that's also fine. Okay? All right, but that's the equation of our line, and it's similar to what we did before, except we're just using a different way to get the derivative. That's the only added feature in here. Okay. Okay, we'll do one more example here. All right, the last example that we will do, similar to the one we just did, our goal will be write the equation of the tangent line at the point x equals 8 for this big old mess of a function here. Okay? All right, now this one I don't know what it looks like. I have no idea what this graph even comes close to resembling here. Okay? But our goal is to find the slope or the equation of the tangent line at x equals 8. Okay? All right, now what's the only thing that we weren't given on this problem that we were given right away on this one? We were given the y coordinate, right, okay? In this example, we're not given the y coordinate, but what could we do to figure it out? Yeah, sure, plug in 8 equals x, and let's just see what the answer is, right, okay? So if we go into this function and we sub in x equals 8, 8 squared minus 64, 8 to the 2/3, y to the 1/3 equals 12. Okay, what happens to this first term right here? It zeroes out, right, because this is all just a bunch of big zero here. All right. So now the question becomes, okay, well, what's 8 to the 2/3? Well, that's just a 4, and y to the 1/3 equals 12. So the equation simplifies quite a bit. Okay, and so we divide by 4 on both sides, and then how do I get rid of that 1/3? Cube both sides. So I'm going to raise both sides to the 3rd power. So y equals what? 27. Okay? All right. So in this problem, the ordered pair that we care about is 8, 27. Okay? All right. Now that we're finished with that, now the problem, very similar to what we did over here. The only thing left to do is figure out what the slope is. Okay? All right. This one will be... This is just will take a little bit longer. And the reason it'll take a little bit longer is what do I need to use out here? I'm going to have to do a product rule there, and what am I going to have to do in here? Another product rule, right. So I just got a couple of product rules. Okay, so it'll take a little bit longer, but the concept is still the same. All right, so the first piece is just y over 18. What's the derivative of this in parentheses? 2x. Okay, so that wasn't so bad. Okay, plus the second term times what's the derivative of the first? Okay, the derivative of this, I can think about this, if I want to, I can think about it as 1 over 18 times y. And the derivative of any number times y is just the number, right? So 1 over 18. But now, since I was doing the derivative with y, I need to multiply by what? dy dx. Okay, so here's the first times the derivative of the second. Here's the second times the derivative of the first. Okay. All right, now I go to the second product rule. Okay, I've got the first term. What's the derivative of the y to the 1/3? 1/3 y to the negative 2/3 times dy dx, right? Okay, plus the second part of the product rule times what's the derivative of x to the 2/3? 2/3 x to the negative 1/3. Okay, and then the derivative of 12 on the other side is 0. Okay. This is one example, and that's kind of why I showed you to do the problems this way over here. Okay, this is one example where I would not waste my time solving for dy dx, because this is quite a mess right here. Okay, I think it will be much easier and more efficient if we just start plugging the numbers in right away and then do our solving at the very end. Okay, so let's start plugging in numbers here. Okay, 27 divided by 18. 1.5. 2 times 8. 16. All right? Plus. Okay? Also notice what happens here. If I plug in 8 here, what happens to this whole term? It cancels out. It zeroes out. So had I gone through and solved for that, I would have done a whole bunch of extra work that's really just going to turn into a 0 anyway. Okay? So that's just 0. All right. 8 to the 2/3 is 4. I've got a 1/3, and then y to the negative 2/3. Okay, 27 to the negative 2/3 should be, okay, 27 to the 2/3 would be 9, and so if it's got a negative, it would be 1/9. Okay? dy dx stays here, plus y to the 1/3, that's 3, 2/3, 8 to the negative 1/3. Okay, what's the cube root of 8? What times what is 8? 2, and so if it's got a negative, that would make it a 1/2. It would move it to the denominator. Okay, so that 2 goes to the denominator. All right, equals 0. Now this is a much more manageable problem to solve for dy dx. Okay, all right. 16 and 1.5. This would be 24. This would be 4/27 dy dx. Let's see, this is the 3's cancel, the 2's cancel. That's just a 1, isn't it? Okay, so that's 0. 24 plus 1 is 25. So I can move that 25 over to the other side. And then my last step is, how can I get rid of this 4/27? Okay, I can divide off 4/27, or I could multiply by 27/4, which is the same thing as dividing by 4/27, right? So either way, whatever this answer comes out to be when you multiply it out, that is your slope at this point that we care about. Okay? And so then the final part of the answer would be, now I just need to write out my equation. Y minus 27 equals whatever this slope comes out to be times x minus 8. Okay? And I went through and tried to pick out the most difficult problem I could find, and this is the one I came up with. So yes, this is the nastiest one you're going to run across. Okay? But I think if you just try to take it a step at a time, that's the key. Try to break it down one piece at a time. It can be done. But like I said, it's not the easiest thing. Okay? All right. Are there questions at this point? Okay. All right. That'll work for today on implicit differentiation. Okay. Your assignments are posted on Blackboard.